Yes, Yoshitaka, just give us a second. So I'll be switching your slides. You'll have to tell me when to advance. We hear you fine. And I'll be just watching from my screen with your presentation. And hopefully, do you see the screen projected so that you can?
Yes.
Then we all set and I'll be just quiet and you please go ahead.
All right. So hello, everybody. I hope you're enjoying Bangalore. I wish I could be there with you, but unfortunately I had to cancel my trip at the last moment. But I'm glad that at least I can give you a remote talk on this subject. So this is the title that I was given, this angular momentum distribution in the proton. To be more precise, so there are spin and the orbital angular momentum. So, but spin was covered by the previous speakers. So I mostly talk about the orbital angular momentum. And by distribution, I mean the distribution in X. One can also think about spatial distribution and momentum space and coordinate space distributions, but there will be a dedicated talk later today, so I will not go in there. Next slide. So there was already a nice talk by Christine yesterday, but let me just go through the usual ritual. So the proton has spin 1/2, and the proton is not an elementary particle. And from these two facts, we immediately conclude that the spin of the proton must be decomposed or can be decomposed into the helicity and orbital angular momentum of quark and gluons. So this 1/2 is ultimately decomposed into the quark helicity delta sigma, the gluon helicity delta G, and the orbital angular momentum of quark and gluons. And this is called the Jaffe-Manhart sum rule. And there is another sum rule called the G sum rule, but I will only talk about the Jaffe-Manhart sum rule in this talk. And this delta sigma is 1 in the naive quark model, but in the next slide, when you do the measurement from polarized TIS, this delta sigma was found to be very small, much less than 1. But more recent measurement gives some bigger value, but it's still much less than 1. It's about 30% of the proton spin is coming from the helicity of the proton. And the question is where does the remaining spin comes from? Next slide. So that's why experimental has been vigorously working on the remaining components of the spin puzzle, and so this is actually the major achievement of the RIC spin program, that they eventually help to constrain that the delta G, which is given by as a integral from 0 to 1 of the polarized gluon distribution function. So there are 3 active collaborations, DSSV and NPDF and JAM, and they all point to a non-zero value of the delta G for given interval of the X integrations. But in fact, there will be a huge uncertainty. There is a huge uncertainty at the moment. There is a huge uncertainty from the small X region. This is part of the reason why the small X community started to look at this problem. This is one of the reasons why people started to look at this problem. So next slide. And here it's one of the one particular interesting result is it's a reanalysis of the region intercept, which was last year. And so there is a classic work by Bartels, Reif, and Rishkin, and this is from the so-called infrared revolution equations, where they resummed the leading small x logarithm to all-order in perturbation theory, and from there they determined the region intercept for the polarized quark and gluon distribution function. And this has been done in the 19th. But just last year, Yuri Kovchikov and his student revisited this problem, and they find the discrepancy. It's a tiny discrepancy which first appears at 4 loops in perturbation theory. So you can see the first 3 orders are completely in agreement, but the 4th order, the coefficient differs by 2%. And this is a very small difference. So if you look at if you recast this into the region intercept, then you can see this only the less than 0.1% difference in the radial intercept. So phenomenologically, this will not make any difference, but conceptually, this is very interesting. And I remind you that this anomalous dimension has been computed only to 3 loops. So at the moment, we don't know which one is correct. So we have to wait for the real calculation of the splitting functions, which is not yet available. Next slide. And coming back to the large X helicity distribution, so most of the analysis is based on the next leading order global analysis, but very soon, probably, we will hear from Vernon and his collaborator that the fast next leading order global analysis for the helicity PDF. So this is the this is a slide that I stole from Werner's talk at the SPIN conference in last fall, and you can see the very fast next leading order global analysis for the helicity PDF. So the helicity PDF, there's lots of interesting progress, and you can consistently improve the accuracy of the determination of helicity PDFs. So next slide. So I will not talk about the helicity anymore, but I will talk about something else. So Raju has an elephant, but this is a different elephant in the spin physics community, and that is the orbital angular momentum. Well, it's an undeniable fact that experimentally we know nothing about the orbital angular momentum. And however, as is clear from the Jaffe-Manoha sum rule, the spin sum rule cannot be complete without understanding OM. That's clear. And I want to remind you. I want to remind you that the helicity is not a conserved quantity. So you can see only the sum of the 4 terms. So all these terms depends on the Q square, the renormalization scales. And if you only sum the quark and gluon helicity, that is not RZ invariant, right? So that means that even if the orbital angular momentum is 0, accidentally at some value of Q squared, and if you do the de Graaff evolution, then it will be non-zero if you go to the other values of Q squared. So the orbital angular momentum is always there, and it has to be somehow quantified. So I want to talk about the OM in the rest of my talk, but I want to start with very basic. So next slide. So what is OM? So what exactly it is? So if you look at the paper by Jaffe and Manoha in the 1990, then you can find the expressions like this. And so there's a quark and gluon orbital angular quark and gluon orbital angular momentum, and there is an obvious deficiency. So this nabla is an ordinary derivative. It's not a covariant derivative, so this is not gauge invariant. And so you have to understand this expression in the light cone gauge, a plus equal to 0. So the question is, how do you make this gauge invariant? So you might think that you just need to replace this ordinary derivative with a covariant derivative, but that's actually not the answer. And in the gluon case, it's even more problematic because you have this gauge field AK, and that is obviously problematic from the gauge invariance point of view. Next slide. So people still say that Jaffe-Manoha sum rule, this orbital, all these things, Jaffe-Manoha decomposition is not the gauge invariant. However, the gauge invariant completion of Jaffe-Manoha is understood, and many years ago. So this is exact definition of orbital quark and gluon orbital angular momentum. It's gauge invariant. And however, it is a non-local definition. So I said that the ordinary derivative should be replaced with this D pure, which is different from the covariant derivative. So this is, it looks complicated, but this is how it works. All right, next slide. And one particularly interesting way to characterize orbital angular momentum, and also from practical viewpoint, it's important to characterize OAM in terms of the so-called Wigner distribution function. So this is so this is a phase space distribution of partons in QCD. So this is a 5-dimensional object. So we have a phase space distribution in both in momentum and transverse coordinates. And then you can define the OAM like in classical mechanics. So it's a B cross K. This is a classic definition of the orbital momentum weighted by this Wigner distribution function. So this looks like, so as long as Wigner distribution is gauge invariant, then this orbital angular momentum is also gauge invariant, obviously. Next slide. And in practice, it's more convenient to do the Fourier transform to the momentum space. So B equals to delta, it's the momentum transfer. Then it's called generalized TMD, which you can decompose in the tensors. So F11, F12, F1. So these are the independent components of the generalized TMD. And the important thing is this F14, the last term here. And if you take this, the second moment of this F14 GTMD, then you find this is quark and gluon orbital angular momentum. Next slide. But the question is, which OAM is this? And because there is an ambiguity in how you make the Wigner distribution gauge invariant. So there are there are 2 points separated both along the light-like direction and also along the transverse direction. So there are different. So how you connect these 2 points is not unique. And if you go around this staple link shaped Wilson line, so if you first go to the light point infinity, then it comes back. And if you choose this, if you make this choice, then what you get is the Jaffe-Manoher canonical orbital angular momentum. But instead, if you take the straight line from these 2 points, so starting from this point and that point, if you take the straight path, then what you find is the orbital angular momentum of the kinetic of the G subgroup. So this so it's a different depending on the shape of the Wilson line, you get a different orbital angular momentum. Next slide. This actually makes a quantitative difference. So this is the latest calculation by Michael Engelhardt and his collaborators. So what is plotted here is the OAM as a function of the length of the Wilson line in the light cone direction. So 0 means so they are on the same place. So this is a G's definition of the orbital angular momentum. But this distance goes to infinity, then you approach this Jaffe-Manoher definition of the orbital angular momentum. And then you can see, so the difference between the height of these 2 curves between the center and the infinity, that is you see the difference, and that is a reflect of the Wilson lines extending to infinity, and that picks up some phase, and that makes this quantitative difference. All right, next slide. So I want to talk about the distribution. So that's the title of this talk. So I want to talk about the X distribution of the orbital momentum, and that is, of course, a natural and in fact a necessary thing to do, because you know this. If you want to measure this delta sigma, then you first have to measure this polarized quark distribution function as a function of X, and then integrate over X to get this delta sigma, and same with delta G. You first measure the polarized gluon distribution function as a function of X, and you integrate over X. So if you want to measure the orbital angular momentum, then you have to first measure this function as a function of X, and you may integrate by X. So you have to first define the X distribution for the orbital angular momentum, and that can be done in several different ways with equivalent result. But the most intuitive way is to simply get rid of this dx integration in the definition of the orbital angular momentum that I showed you before. So I just get rid of this dx integral and identify the integrand as a Proton distribution function of the orbital angular momentums. And this is I think this is the most intuitive way to define, and it's actually the correct way. And you can write it more So next slide. You can study this distribution in more details. Okay, so the point is that this PDF is actually a T3 PDF, so like a G2 G2 distribution function. And if you're familiar with the G2, then you know that the G2 is decomposed into the so-called one-zero recheck part and the genuine T3 part, which is related to the quark-gluon quark correlation function. And one can do the same thing for the orbital angular momentum. So this is a complete deconstruction of the orbital angular momentum distribution for quark and gluon. So there is a one-zero recheck part, which is related to the two GPDs, so H and E, and the H serialized polarized quark distribution function. And there is a genuine T3 part, which is given by this quark-gluon quark correlation function. And we can do the same thing for the gluons, and in that case, which involve the three gluon correlation function. So the definition of the PDF is exactly it's known. Next slide. And since we know the distribution, we can also think about the evolution of the distribution. And since there are two parts, but the one-zero recheck part and the genuine 2-3 parts, we can consider the evolution separately for these two parts. For the one-zero recheck part, the leading order result is well known. So this was understood in the 90s. And since we have exact relation, we can generalize this to all orders in perturbation theory. And in fact, the evolution of this OM is completely, the one-zero recheck part is completely determined by the evolution anomalous dimension of the polarized and unpolarized PDF. So if you know this, right now we know this anomalous dimension to 3 loops, and then we know the evolution of this one-zero recheck part to 3 loops. Thus they are governed by the same evolution equation with some particular linear combinations. Next slide. The evolution of the genuine 2-3 is much more complicated because it involves the 2-3 operators, the quark, gluon, quark, and 3 gluon operators. But for this, we can borrow the wisdom from some other areas of physics. And in fact, these are exactly the operators that appears in the so-called transverse single spin asymmetry, the Ephraimov-Teref-Schusterman function. It's called the ETQS function in that context, and the evolution equation for these operators is known. So now I'm talking about the longitudinal spin polarization, but this ETQS is for the transverse spin polarization, but that doesn't matter because after all, the evolution is determined by it's a property of the operators and not the external proton spin state. So we know the evolution equation, and there is a numerical code developed by Pyrenees, and we can do this evolution in the Q-squared evolution of this distribution function. So the evolution of OAM definition is fine. The evolution is understood at least one loop. Next slide. And next, I want to talk about the small x behavior. So here there is a very simple argument about what happens to the orbital angular momentum at small x. So suppose you have a high energy quark, energetic quark. This quark emits a very soft gluon. So the momentum fraction x is much less than 1. Now, from the quark's point of view, nothing happens. So because this gluon is so soft, and then this is a vector interaction, so the spin of the quark doesn't change. So nothing happens to the quark. But this means that, so this gluon, emitted gluon has both spin and the orbital angular momentum, but they have to cancel each other because just from the angular momentum conservation, right? And you can see that from the evolution equation. So if you look at the evolution of the orbital angular momentum for the gluon and the helicity, you have an opposite sign contribution from the parent quark spin state. And this means that there is a cancellation between helicity and orbital angular momentum at small x. You can see that from this very simple argument. Next slide. And here is some demonstration by the left-hand side. It is a calculation by Asmita and her collaborators. So So they use a single quark dressed by one gluon. So this is exactly the situation that I described in the previous slide. And you can see this is what is plotted here is the sum of the orbital angular momentum and the helicity of the gluons. And as you go to the small x region, then the sum goes to 0. So there is an almost perfect cancellation between the helicity and orbital angular momentum that I explained to you. And one can also study the D graph. One can solve the D graph equation. So, so on the right-hand side, this is the solution of the D graph evolution equation. And you can see the almost perfect cancellation between delta G and the orbital angular momentum as you go to the small x region, which corresponds to the right, going to the right in this plot. And there is also a cancellation between quark helicity and quark orbital angular momentum, which is shown in these small plus minus curves. All right, the same thing happens for the quarks. Next slide. And so this is a very simple argument, but one can generalize this argument to all orders. So because we have this exact formula for the gluon orbital angular momentum. So if you look at this the expression, then one term stands out at small x. So this is the integral of this delta G. And so we expect that this term dominates if you go to the small x region. So suppose this delta G goes like 1 by x to the power of alpha, then you just plug it here, and you immediately find that this orbital angular momentum is proportional to the delta G with a prefactor which is negative. And this minus sign is represents the cancellation that I talked to you before. And so this result is very general, and again, you can actually confirm it in the double log resummation scheme, resummation. And also very recently shown by Yuri and his student that, and also the students in the paper, that this relation is robust even after including the genuine twist-free effects, which is presumably included in their approach. Next slide. So there will be cancellations, a strong cancellation between helicity and orbital momentum. So and my final topic is observable for the orbital angular momentum. And frankly speaking, this has been non-existent, but until recent. There are actually several papers that came out for the. However, we are still at the level of identifying processes that are sensitive to the orbital angular momentum at leading order. And so this is indeed a very difficult problem because the observable is twist-free. And especially for twist-free, it's very difficult to establish a factorization, for example. And also this OAM involved the GTMD, and the factorization for GTMD is not understood. But with the exception of one paper, which appeared last year, where they seem to have shown the factorization for one particular process which involved the GTMD. But so this is encouraging the process progress, and hopefully this kind of generalized to other processes. So next slide. So here's our proposal that we did in 2 years ago with Shohini Bhattacharya, Reno Busari, and another paper is in preparation. So this is if you want to measure this orbital angular momentum, remember this is just B cross K, right? And so yeah, but B, so you have to be sensitive to B and K. Now B is simple because B is conjugate to the delta, which is a proton momentum transfer. So you need to look at the exclusive process where the proton scatters elastically. So that's a minimum requirement. Now, K is a bit tricky. So this means that you need at least one additional momentum scale, momentum transfer, momentum scale in the process. And one example is this, and also the proton has to be longitudinally polarized. And then one example is this longitudinal double spin asymmetry in diffractive, exclusive diffractive digest production, where this jet transverse momentum reflects this K-pop information. So on the proton recoils. So you have delta from the recoil proton and K from this jet transverse momentum, or at least they are correlated. And the cross section is a double spin asymmetry, so it's proportional to the helicity of proton and lepton. And we propose to look at the cosine correlation between the lepton scattering lepton plane and recording proton momentum. And the cross section is given by the interference between the twist 2 and twist 3 amplitude. As I said, this is a twist 3 observable, and it's also interference between the longitudinally and transversely polarized photons. Next slide. So, we did the computation that's 2 years ago, and at that point we identified 2 contributions, but in fact there is a third. So there is a third contribution. This is a new development, or in other words, we missed this 2 years ago. So the first contribution is OM. This is what we expect. So we pick up the unpolarized proton GPD. So this is a twist 2, and we pick up the orbital momentum from the compressed conjugate amplitude. Another contribution coming from the helicity. So you pick up the GPD unpolarized gluon from the amplitude, and polarized GPD from the compressed conjugate amplitude. This sounds like a twist 2, but we pick up one factor of delta from the hard factor. So this is called the kinematical twist 3 effect. So the involved distribution is twist 2, but it's actually a twist 3 contribution. So this is what we identified 2 years ago, but more recently we realized that there is a third contribution, where you pick up the unpolarized helicity distribution from the amplitude and the so-called spin orbit coupling from the compressed conjugate amplitude, and that is new. And this is something, it's not something this not understood, and nobody knew how this function behaves. So next slide. So what is this gluon spin orbit coupling? So this is one of the GTMD. So this polarized GTMD. So you have a polarized gluon operator here with the epsilon ij, and this G11 component. And now this G11 is multiplied by this correlation, which looks like an orbital angular momentum. So this is like a transition amplitude. You start from the helicity operator, and you end up with the orbital angular momentum type correlation, and the strength of this transition is this G11. And this is called the spin orbit coupling in the literature. And very little has been known for this function, but in this work, we worked out the one-zero check relation using the equation of motion, and we find the relation between this spin orbit coupling and helicity and unpolarized gluon GPD and PDF. And we find this function is negative. It's actually negative of the gluon distribution function. And this is it's a reassuring, because if you look at this paper by Lose and Pasquini, where they argue this spin orbit coupling. So the physical meaning of this spin orbit coupling is that this is positive if the spin and orbital and the momentum are aligned in the same direction, but it's negative if the spin and orbital and the momentum are anti-aligned, right? And as I said before, the spin and orbital and the momentum cancel at small x. So at small x, you should expect a negative sign for the spin orbit coupling, and that is exactly what you find from this equation of motion relations. And that is contributing to this double spin asymmetry paper. So we have to revise our previous prediction. Next slide. So I just added one more curve, which coming from the spin orbit correlation. And numerically, it is actually large, so we have to worry about it. But the good thing is that I think this function is better constrained than the, so you have to subtract this anyway if you want to measure this orbital angular momentum, but I think this function is better constrained compared to the other contributions. but more work is, of course, obviously needed. And put in another way, another way of viewing this, that spin orbit correlation is itself interesting, observable. So there's been very few discussion of this in the literature, and then let alone experimental observable. But I think so this observable is sensitive to the spin on OM and their correlation. So this kind of very interesting. And just one side remark. So as you can see, so this QPUB, this symmetry as a function of QPUB, this is actually a jet transverse momentum. And it's I'm showing numbers like 1 GeV and 2 GeV, which is too small to be reconstructed as jets. And this is one of the deficiency of the previous proposal. But we find a new proposal which avoids this problem. So instead of measuring dijet, we can reinterpret this process as the semi-inclusive diffractive DIS. This is something we proposed 2 years ago. I proposed with Boen Shao and Feng Yuan. This is similar to the diffractive DIS, except that you measure a particular hadron species out of the diffractively produced system. And this is still challenging, but at least we don't have to reconstruct jets. So this will be also discussed in the upcoming paper. Last slide, next slide. So here's the conclusion. So the orbital momentum is an essential component of the spin-sum rule. And I remind you that helicity is not a renormalization group invariant. So OM is always there. And the proton spin structure is one of the most important topics in ESG, and especially there's not much discussion on OM, and I think I'd like to see more discussion on orbital momentum. So, and there are some other projects. So I've only talked about the gluon orbital momentum, but this very recent paper discusses the quark orbital momentum. So thank you very much.
Thank you. Let me see if there are questions here. I can grab a couple. Okay, there will be an option maybe to send some by email, or Asmita, you have a question? Mm-hmm.
Yeah, Yoshitaka, this is Asmita. Can you hear me?
Yes.
Yeah, thanks for the talk online. So I was just wondering, so in the slide where you have shown that this cancellation of the gluon intrinsic spin and the orbital angular momentum as x goes to 0, can you please go to that slide?
Slide number 19, I think.
Yeah, so on the right-hand side, could you please remind me what this is also a perturbative calculation, the right-hand side plot?
This is a solution of the DGLAP.
Oh, this is directly from that equation.
Yes.
Okay, thank you.
All right, thank you very much. I don't see any questions here. And that's the end of our morning session. Thank you to both speakers, and